So we've been looking at some orbital mechanics. We had just finished doing a question that was a lot of work, no pun intended. Some neat patterns. You don't need to have this memorized. This is kind of a handy built-in error check that I've noticed. So it says this: using the expression for orbital speed, which was the square root of big G big M over R, we derived that by saying gravity is what's pulling us in a circle, and we got the V by itself. Prove that the kinetic energy is half the magnitude of the potential energy. So cosmic potential energy is negative big G big M little m over R. You found it okay, Colby? Okay. It says, prove that the kinetic energy is half as big as that magnitude. So it'll be positive, but prove that it's half as big as that. Well, first of all, Nina, what is our equation for kinetic energy? What's it been ever since Physics 11? Ke equals. But V in orbit is that. So I'm going to plug that into there now. When I square the V, I think the square root is just going to cancel. And so I'd end up with 1/2 m big G big M over R. And if I just rearrange the order that I've written things in, I have a 1/2, a big G, a big M, a little m, and an R. So here's the question. Look at what we've just written. Look at the potential energy equation. Dylan, is the kinetic energy half as big as the potential? But magnitude positive, so that's why I said magnitude. How is that handy? You know what? If I'm finding the potential energy in orbit, and you often are using that ditto mark method and you write it down, and I find the kinetic energy in orbit, if I happen to notice that my kinetic energy is half as big as that other number, yay, I did both of them right. B says, so yeah, we proved it just by doing a straight substitution. B says, prove that the total orbit energy is half the potential energy. Total energy? How would I find the total energy in orbit? I think I would take the potential energy in orbit and the kinetic energy in orbit and do what? Okay. Total energy is going to be potential energy plus kinetic energy. Now, potential energy is negative big G, big M, little m over R orb. And kinetic energy is 1/2 big G, big M, little m over R orb. I'm using what we derived in part A. So I don't know if this is stuff that you want to add to your blue sheet or not. Jacqueline, you can. I've never been forced to pull this out of my pocket to solve a question. What I have done is, as I've been solving questions, go, oh, hey, I notice, by the way, the coefficient here is technically a 1, and so it's -1 something plus 1/2 something, but they are like terms. Each thing has a big G, a big M, a little m, and an R orb. And so you do end up with -1/2 big G, big M, little m over, which is half of the original potential energy. You can survive just fine without it. It's handy. Oh, and then part 3, which I, for some reason, I'm using letters for, but okay, says, prove the total energy, that's this, is the opposite of the kinetic energy. I think we have. This is positive 1/2 big G, big M, little m over R orb. This is negative big G, 1/2 big G, big M, little m over. So, prove it. We kind of did. So, just for the record, you can survive without this, but I sometimes use it as a handy error check in my calculations. Now, this doesn't work if you're doing change in potential and change in kinetic. That pattern doesn't hold. But if you happen to be staying in one location, you should find that your universal gravitational potential energy and the kinetic energy required to stay in that location, the kinetic energy will be half as big and the total energy will be half as big. So let's walk through all of this. This is about every single example I can think of, every way I can kind of mix and match. A rocket at rest on the Earth's surface blasts off from rest. I would probably mentally underline the word from rest. Rises to a maximum altitude or height. Write equations to calculate the work done by the engine. Assume the rocket begins and ends at rest. Looking at the picture, Victor, does this look like it's in a stable orbit? Say no. If I want you to be in orbit, what I'll do is I'll turn the rocket sideways to show you that it's meant to be in orbit. So we can't go, gravity is what's pulling me in this. Oh, in fact, what's this question wanted me to write? Calculate the what? Work. So it's going to be change in potential. Why didn't I bother writing plus change in kinetic? Because it said assume the rocket begins and ends at. Okay. And so here we would end up with negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. And I should make a little note here. Capital R final is R plus H. Sometimes I'll give you the height or the altitude. Read carefully. Sometimes I'll actually give you the distance from the center of the planet if I just want to save you a line. And literally, that's what it is. Often I'll look at an answer key and I'll add up a number of marks and I'll say, I can save them one step. I'll give them the radius instead of the height, and then they don't have to bother adding them together. I saved them one line of work. Why won't this keep it in a stable orbit? No, what kind of energy? No, what kind of energy? Okay. No KE to have the orb. Yeah. And I hope this is something you've wrapped your brain around. A lot of people without a physics background will just say, oh, there's no gravity in space. That's how satellites stay up there. There's a lot of gravity up there. Okay. What if I wanted to slightly twist this? So this first example, A, would figure out how much energy it would take to get something up there, how much rocket fuel if I wanted to actually build a rocket. A rocket moving at speed V at liftoff, so now we're not starting and ending at rest, rises to a height h with no engine use. So let's assume we fire our engines up and launch and then shut them off instantly and coast the rest of the way. Write an equation to calculate the maximum height using conservation of energy. How would I know to do this with conservation of energy if they asked me to find the height? There's a change in height, there's a change in speed, there's a yucky curvy path. You could do this with a work equation, but what you would do is you would let work equal 0 because there's no outside source of energy. I would just say, you know what? KE initial plus PE initial equals KE final plus PE final. Although it did say assume the rocket ends at rest, so we could nuke KE final. I would end up with a half M V initial squared plus negative big G big M little m over R initial equals negative big G big M little m over R final. And as far as I'm concerned, I can either tell you my launch speed and ask you to find the final distance from the center of the planet, or I can give you the final distance from the center of the planet and say find the launch speed. In this equation, I would not try and get the V or the R final by itself first. What I would do is I would get the term by itself, crunch the whole other side, turn the whole other side into a single number, then I would probably get whatever I needed to by itself. This one's a bit trickier because the R is on the bottom. Oh no, we've dealt with R's on the bottom before. I would turn this all into one big number and then multiply the R to the top, move this number to the bottom. A rocket moving at speed v at liftoff near the Earth's surface barely escapes Earth gravity. Did they say escapes? This is going to be what we called escape velocity, should be called escape speed, with no additional engine use. Write a conservation of energy equation that would allow us to solve for V. Note we call this escape velocity. So we did this last class, and we said it starts out with conservation of energy, G. But we said what was weird about this equation, James, is out at infinity, that was 0. And we wanted to end up at rest. And so what we wanted to have was a half mv initial squared plus negative big G big M little m over r initial equals 0. Although we then plus this over. A half mv initial squared equals positive big G big M little m over r initial. So what's fair game here? As far as I'm concerned, probably I'll give you the mass and our distance from the center, and you can find VI. But my point is I can give you any two of those, and you can find the third one. I could tell you the escape velocity and say, hey, what's the mass of the planet? Oh, okay. I could tell you the distance from the planet, what our escape velocity is required to leave. I could tell you the mass of the planet, what our escape velocity is, and say, how far away are we from the planet? Okay. Oh, by the way, up here, I probably should have technically said that that happens, yes? What else can we do? Victor, are we in orbit in D? Okay. As soon as I'm in orbit, I have the handy-dandy gravity is what's pulling me in a circle. Here, how much work will the engines do? It's going to be the same as Victor said earlier, except now I'm going to have a change in kinetic. Okay? Where the change in kinetic is going to be a half m v orb squared. I might give you V orb. Yay! Or you might have to use gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals mv squared over r. You might have to actually calculate that orbital speed is the square root of big G, big M over R orb. Some of you may have memorized that during this unit, but hey, by the end of the year on your final exam, you've forgotten it. This is how we can derive it, which is why I always tell you, I'll teach you how to derive everything. Let's not memorize stuff. This question is a lot of work, both in terms of you'll get a big answer, usually in the 10 to the 10th, 10 to the 11th range. If you're around the moon, which has less gravity, usually in the 10 to the 9th, 10 to the 10th range. And it's a lot of work because this basically took a whole page, especially if I didn't give you V. E. A satellite moving at speed V at a distance big R from the Earth center falls to the Earth's surface. How fast will it hit the Earth? How would I calculate that? Work? Colby? Did this question mention the word work? E, you can see the word work somewhere in part E? This part E. Do you see the word work anywhere here? Don't use work. So how would I solve this one? What approach would I use? Colby, what do you think? Yeah, good, thank you. There's a change in height, there's a change in speed, there's a yucky curvy force, that graph that we sketched. So I would use KE initial plus PE initial equals KE final plus PE final. This would modify into a half mv initial squared. I might be nice and have the initial speed be 0, but realistically, in real life, asteroids or satellites are never at speed 0. They always have some initial speed. So I might, because I like to do realistic questions, give you an initial speed plus negative big G, big M, little m over R initial. That equals a half mv final squared plus negative big M, little m over R final. This one is a little bit different because R final would actually be the surface of the Earth. In most of the other situations, we're ending up there, and so R final is your orbital, or your what distance from the center of the planet, way up there. Here, R final would be 6.38 times 10 to the 6th, or whatever planet we were dealing with. Once again, little m cancels. Yay! What's fair game? I could either ask you where we started, or how fast we're going on impact, or how fast we were going to begin with if you knew both of these. This one is also just a lot of pure number crunching. Be careful with your calculators. I'm trying to remember. I don't know if I would give you a VI. I would probably just be nice and let VI be 0. Or I would have it start all the way out at the edge of the universe. If we start all the way out at the edge of the universe, what would my initial potential energy be? That would be another way just to make sure you understood the concept, but also give you less typing. I might do that. And it'd also just be kind of cool, because you can imagine the asteroid slowly making its way to the Earth. Donna, Donna, Don, until it... Nothing? Okay, sorry. Example 7. Let's put everything together. A satellite is in orbit. Victor, I would mentally or physically underline the word orbit, because that does mean that I can go, gravity is what's pulling me in a circle. What does A want me to find? Okay. Big M. Now, it does show up, don't write this down, in that equation. If I knew the gravitational force that the satellite was feeling, I could solve for big M. Or if I knew the gravitational field at that location, I could solve for big M. I don't think that's going to work. My first thought might be, maybe I can use gravity as what's pulling me in a circle. And so this is what my brain would think. Don't write this down. I would go, okay, big G, big M, little m over R squared equals M. And then I would say, am I going to use the one with the speed in it, or am I going to use the one with the period in it? It's a trick question. Did they give me in the information here anything about speed or period? I can't use gravity as what's pulling me in a circle to find big M. Okay. What else have they given me here? Let's try that equation. So I'm literally going to go, well, P, write this down, equals negative big G, big M, little m over R. Let's do a quick variable check. William, do I know the potential energy? I know big G, 6.67 times 10 to the 11. Do I know little m, mass of the satellite? Do I know R? Oh, okay, this is what I would use. And some of you, I think, saw that right away, but just to let you know, this is how my brain would tackle these. I would go through kind of a mental checklist. Because anytime I see the word orbit, it kind of triggers me. I lean towards gravity that's pulling me in a circle, but that wasn't going to get me anywhere. How would I get the big M by itself? Big M is going to be R times the potential energy negative divided by big G little m. Is that correct? The negative and the big G and the little m would move to the bottom, although a negative just goes anywhere, and the R would move to the top. Okay. So it's going to be negative 8.85 times 10 to the 6th negative 6.55 times 10 to the 10th, all over 6.67 times 10 to the negative 11, 965. It's a planet, so I'm expecting something in like the 10 to the 20th or 10 to the 30th-ish range, I think. Let's see. Negative 8.85 times 10 to the 6th times negative. I guess I could have just canceled out the negatives, which is good because the mass of my planet should be positive. Divided by bracket 6.67 times 10 to the negative 11 times 965. Typo, Mr. Dueck. You get 9.006 times 10 to the 24th. Anybody else? Yeah? Okay. I'm going to carry the extra couple of sig figs because I think I'm going to use this. So 9.006 times 10 to the 24th kilograms. What's the mass of the Earth? 6 times 10 to 5.98 times 10 to the 24th. So roughly 6. This is roughly, what, 50% heavier than the Earth. Earth-like planet. Okay. Dylan, what's B want me to find? Orbital speed? I think now I'm going to try going gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals mv squared over r. Now, the other thing I could have asked, instead of the speed of the satellite, I could have asked for the period of the satellite, or I could have given you the speed or the period and said find the radius of the satellite. Little m cancels. One of the r's cancels here. Oh yeah, we've seen this before. Orbital speed is the square root of big G, big M over r. So if we crunch this, it's going to be the square root of big G, 6.67 times 10 to the negative 11. Big M, I'm going to write 9.006, but you know I'm going to use my answer button because it's still stored on my calculator, Dylan, if that's okay. And R was 8.85 times 10 to the 6th. .67 times 10 to the negative 11 times, answer button, divided by 8.85 times 10 to the 6th, square root of that. I got 8,238.667, 8,240. Anybody else? Yeah, nodding. 8,240 meters per second. Cool. Johnny, what does C want me to find? How can I find that? How do I find kinetic energy? No, we don't need to even go there. Just straight kinetic energy. What's the equation? It's on your sheet. Yeah. Now, folks, a half mv squared will work. However, if I was clever, I could just divide this number by 2 and make it positive. So let's see if that little trick, that pattern that we looked at, works. I'm going to do it Johnny's method, the long way. So I'm going to go KE equals a half mv squared, especially because I have v stored on my calculator right now. So it's going to be 0.5. What was m? 965? I'm going to write 8,240 squared, but I'm going to use my answer button. If I go 0.5 times 965 times answer button squared, I get 3.275 times 10 to the 10th. And if I double that, is that the magnitude of the potential energy that they gave us in orbit? Bang on exactly. Okay? That's where the shortcut can sometimes be handy. Okay? In fact, what I could have done, William, for part B, instead of going gravity is what's pulling me in a circle, I could have just taken this number, divided it by 2, and used the kinetic energy equation. Times by 2, divide by m square root. And that would have given me the same answer as gravity is what's pulling me in a circle. 3.275 times 10 to the 10th. Joules. I'll put the whole thing in there so that you can see it is exactly half. And again, Maddie, let me emphasize, you don't even need to memorize that. You can survive just fine without it. It's, you know, it's nice to have in your toolbox, but it's a pretty obscure tool and you really don't need it. It's just handy. I think there was a D. Oh, total energy. I'm going to write negative 3.275 times 10 to the 10th joules because I seem to recall that the total energy, this is what you missed, but that don't freak out, was the same as the kinetic, but negative. But how would I find total, Nina? You answered this earlier. And so if I actually went negative 6.55 times 10 to the 10th plus positive 3.275 times 10 to the 10th. Yay, I got the same answer. And was that much longer than the shortcut, Victor? Not really. And this is why it's a nice shortcut, but meh. What's your homework? Number 1 and number 2. Three is good. 5 is good. Please notice they gave you an altitude and in kilometers. You'll need to multiply it by 1,000 and then change it into a radius. 8 is good. You can skip 6 and 7. Nothing? Okay. 10 is good. 12 is good. 16 is good. 18 is good. 19 and 20. There's not going to be any homework next class aside from a take-home quiz.